All right, thanks everyone for coming back from coffee quickly. So this is where I sort of stopped last time, where I ended up with showing a map of galaxies as well as dark matter. So today we are going to go and try to look at a bit more detail. So some of these things might seem technical, and if you're doing sort of a model building exercise, you may not need to use this kind of details, but if you're trying to come up with new ways to probe certain aspect of model, this will help you think about what are the possibilities. So that's why I wanted to cover that. So I wanted to talk about a little bit more about how this surveys happened. How do your galaxy survey happen? So this is an image from Hubble Deep Field. I'm sure most of you must have seen this image where you see great many galaxies with lots of details and some beautiful colors as well, right? This looks like there are also some artifacts which you can see, diffraction patterns and things like that. But there are big galaxies and there are small galaxies and of different shapes and different colors. But the color of these galaxies in images, colors in this image is actually something not very easy to get in. It's a complicated process. How do we assign colors? Because this is not what we observe, right? So if you're used to using digital camera, you might think all images comes with color, but that's not true. For all astronomical images or any cosmology survey, the image do not have any color. And what do I mean by that? You basically have a map of intensity, and that's what you observe. So how do you get to color? What are the kind of things you need to do, and why do you need to get to color, and what are the differences? Why can we do this in digital camera but not in telescope? Is some of the things you might want to think about, and probably you'll get some idea of that. But if you actually go to a dark sky region, if some of you have done that and just see the sky from naked eye on a mountain range, you'll see something like this. And this image is very different from the image I showed you in the previous slide, right? So the previous slide was Hubble Deep Field. So it's taken from space through using a big telescope, and it's a very deep image. This is just what you see in naked eye. And the difference is here is that you're actually mostly looking at stars in this image as compared to very deep, faraway galaxies in the previous image. What is this field? So what is deep field? Yeah, so if you want to make a deep image, you need to basically look at, okay, imagine you go to a dark region and you look at certain part of the sky. What's going to happen is that when you just start looking, you'll not see much. But as you stare at the sky, you start to see more and more as your eye gets adjusted to it. But there is a fixed amount of exposure time which your eye can take, and then after that, you'll not see any deeper. So what happens is that as you look at things longer, you collect more and more photons. And so the same thing you can do at telescope, but you can do it for much longer time. So you can look at a part of the sky and look at for longer and longer time. As you collect more and more photon, you're going to see fainter galaxies. So Hubble Deep Field is a part of the sky where Hubble telescope have seen for like really long hours. And so we have very deep images, and hence we can see very faint galaxies, which you'll not see if you just open the Hubble, open the shutter for 30 seconds and close it, you'll not see these details of image. That's the difference. Every time you're seeing any survey, any telescope images, there's always a depth involved in it. And depth is about what is the sky condition was and what is the time for each you have observed. But all of this is not always work in the sense that you can't infinitely look at things and go deeper and deeper with the same side of telescope. There are limitations to that. How much time for this deep field? So that I don't know, that you need to look it up, but it's probably at least order of hundreds orbits. So because it's in a space, you're not stationary, you keep moving. And so you count this in terms of orbit, how many orbits you have looked at the thing. But whether how much time it is in terms of number of seconds, I don't know, you have to look it up, sorry. But for a typical telescope, for example, if you have heard of LSST, which is the new survey going to happen, the expected exposure time for SST is about 15 to 30 seconds. It's going to take image, every 15 seconds it's going to click an image. But it's going to observe same part of the sky many times as the sky passes through, or as you go through the years. And so the deep field, LSST will also have deep field. Basically, it will observe certain part of the sky many times, and you can add all those 30 seconds. So if you have 100 times that, then you'll have 3,000 seconds. So if you go up to something like 3,000 to 6,000 seconds in LSST, you'll get deepest image in LSST. So that will be 27.5 magnitude. Right. So now what is in between this image is a telescope. So this is just an illustration, just for illustration purpose. One of the telescopes, this is Mayal telescope, which is a 4-meter class optical telescope. And it has DAISY instrument. So this is an instrument which can take 5,000 spectra at a time. Right. But this is where you can put in whatever instrument you want to put in. Right. You can put a camera, you can put a spectrograph, you can put a some other kind of photometer, and in early days we used to use photographic plate, and so this is a key part of whatever you're going to observe through a telescope like this. So if you take a part of the sky, you're going to go through, so this is basic optics, all of you probably already know. The ray diagram, you have a big collecting area. This determines how much light you can collect, which you can focus, and then finally pass it through eyepiece. Now at eyepiece, you'll have to have detector. The earliest detector were human eyes, right? So you see through, we used to see through our eyes, and that's what was detector, and then you have to record whatever you're seeing. But what kind of detector human eye is? And this will take you into the detector of telescopes. So human eye, if you look at the sensitivity of human eye in sort of a bright normal light condition, not like this, but outside, it will be this V lambda curve. And if you look at what the human eye sensitivity is going to be in terms of in a dark place, like in the night, then that will be this V lambda curve. So our eye adjusts to overall light condition. And so what does this curve means? It means that if I emit 1 unit of light at wavelength of roughly 550 nanometer in the dark condition, I will basically see all of it, right? But if I emit that same 1 unit of light at 500 nanometer, I will only see 30% of it. So our eye doesn't have same efficiency at all wavelength. This is also why whenever you'll see a green light, especially this 550 nanometer light of the same intensity as a red light, you'll always find the green is brighter. Not because the actual source is brighter, just because your eye sensitivity is different. Now this brings a critical point. Same thing happens in our telescope. Whenever we are looking at an object, you will record some brightness, and this brightness is a function of what's the sensitivity. A similar sensitivity curve will be there for the detector, whatever you're using to observe it, right? So now if you want to make any sort of inference for cosmology or galaxy formation, you need to know the sensitivity curve, so figure out what is the true light which is emitted by the galaxy or whatever object you're observing. Yes? So light and dark condition is basically this happens for us if you are, let's say if you just go outside, that's the light condition. If you go outside but in the night and it's dark, that's the dark condition for our. Right. Yeah, so if you have white light versus you don't have any light, that's the response for our eye. And of course, this will be different for different people, but this is a rough mean response you are going to look at. So the same kind of response function is going to be there for all of the telescope. And so you have to make sure you understand and characterize this response very well. And so to figure out what was the true emission from whatever object you're going to look at. So any inference will require a response function like that. Okay, so now in terms of detector itself, what has happened over the years is that it has improved quite a lot. And so this is a very brief history of detector. All of you to sort of briefly look at. We started with, of course, human eye, and after that we Started with photographic plate in 1850s. That's how Polymer Observatory used to observe, and we had huge amount of photographic plate even till 1980s or so, which are all digitized now. So slowly the technology improved. We went to photoelectric photometer, image tube, VDCon, and then came the CCD era. So this was a big change. So early CCD era allowed us to essentially start doing survey kind of things, so survey kind of projects. And then improved CCD from 1990 to 2000, Slow and Detailed Sky Survey. This so this is not exactly the beginning, but this is where things really changed, where we started doing observing objects in order of millions or so. So SDSS did a very wide survey starting from 1990, and then observed. So it went on till 2020, and it observed billions of objects in terms of the photometry and about 10 million objects in terms of the spectra. So that was shown in my plot in the previous slide. And then what we wanted is we wanted to cover larger area faster. So you want to make the CCD big. And so then came the era of mosaic CCD, where you can couple many such CCD together and make a big detector. That was dark energy camera or dark energy survey, if you have heard of. Some of the supernova constraints comes from that. And we are still continuing to develop this technology, and hopefully this will be used for future experiments. For example, LSST I just mentioned, Vera Robin will have CMOS camera, which has this 15-second exposure time. And so 15-second exposure time means you also need to be able to read all the electronics out, right? So anytime you're having a detector, whatever information you're collecting, which is in terms of electron, you need to read it out very quickly. So it has very fast readout, so that sets the limit. All of this is important because let's say if you come up with certain things, for example, transient. So the 15-second exposure time for LSST is essentially limited by transient. So let's say you say there are events where you have to catch a supernova in the first 15 seconds. Otherwise the brightness drops too fast, or there are interesting kind of transient event because of some violent physics you are working with. So what is the best we can do with LSST? We should be able to do 15-second exposure, right? So that will be the state of the art. So that number should be useful for you. And then there are even more modern technologies being developed, but these are not yet used for any realistic survey so far, large-scale cosmology survey so far. Yes. This one? Yeah. So dark energy camera is optical. So most of these detectors are sensitive in optical as well as infrared. So these detectors are not so sensitive about the wavelength. So they generally have pretty wide coverage in terms of wavelength. And that's sort of a good thing, because then using the same instrument, you can measure in a large amount of light, so you can cover a large range of wavelength. But it's also a bad thing, because then you don't know what so what is the essentially distribution of light emitted from the galaxy as a function of wavelength. And so that is something you'll have to figure out, which will be the next topic, how we do that. What is quantum efficiency? Yeah, so that's a very good question. Essentially what we want to do is we are observing photon, and in our detector you're converting that into electron. So you want to quantify how this conversion efficiency is. If you say that if you have n photon and you generate n electron, that's a quantum efficiency of 100%. Right? If you have anything lower than that, so most devices in the beginning had smaller amount, and this efficiency also is a function of wavelength as well. Right? So this also comes in the response function, and so it's essentially quantify what is the conversion of photon, number of photon to number of electron, because that's what then you're reading. Right. So let's say there is a very cartoonish composite image of galaxies which are elliptical and are of different color. If I were to go and take image from any of these detector, all I'm going to find is essentially intensity as a function of position, or in the image. I will have no information. All the detector I showed you, in any of them, you'll have no information about any kind of color or wavelength of the light which you are observing. Okay, so if I were to sort of, let's say, I want to restrict it in certain range of wavelength, then you can design something called filter. And the filter is basically same as what I showed you for our eye. There's a response curve. You can design something. So you must have seen these red, blue, green films. These films are basically act as filter, which allow mostly red, blue or green lights to pass through. So you can similarly design a filter which you can put it in front of your detector so that the light in certain range of wavelength can pass through. So if I have to design a filter, for example, my filter is that I'll allow all the light to pass through at some efficiency, then I'll see this real image will actually look something different depending on the response of the filter, depending on what part of the light your filter is sensitive to. I can design a series of filters. For example, this is called U filter. This is actual U filter used in SDSS survey, and I will see an image like this. I can do G filter, R filter, I filter, Z filter. So these are the 5 filters which are used in, these are standard filters used in Solidity sky survey as well as many other instruments. This is all photometric data. All we are doing is we are taking the same image and saying, okay, if I allow the light only in certain range of wavelength and the shape of the filter, so I will show you that also wavelength dependence, then what will I look at? What it would look like. So I only have overall intensity information after the light passes through this filter. And so it will look different, right? So it's the same part of the sky, same galaxies, it will look different. And if you combine all of that, you can make a color composite image if you understand. So this is how, for example, the image I showed you for Hubble Deep Field is constructed by looking at light in different filters and then combining it and giving it some color assignment. So for any instrument you're going to look at, you need to sort of think about, let's say you want to go and do a survey. You need to think about, okay, what filter do I want to use? Do I want to use any filter at all, or do I want to collect all the light? What is the advantage it's going to give you? All of these will depend on what science you want to do or what kind of questions you want to ask. Some of this might not be important for your science case. It will also affect how fast, how efficiently you can make their observation, how expensive the instrument is. So all of that goes into the sort of part when you try to start thinking about, I want to constrain dark energy to a 1% precision. You start thinking about these kind of things. What kind of filter? Can I just use one of the filter and it's good enough? Because I'm going to detect galaxies, most of these galaxies if there's one filter where I can just see all these galaxies, will that be good enough, or will there be more information and I need to do more than one filter? So yeah, so why this thing is different from, so this is what is called Bayer filter. This is what is used in most of digital camera, right? So I don't know what your phone uses because these are too advanced of a technology, but old digital camera used to use it. But you can check with their phones also uses this. So what this is a grid of filter of red, blue, and green, essentially put in front of the detector, which your digital camera has. And so at each point, at each of these pixels, I will have information about, okay, how much of red, blue, or green light is there. And then when you show an image of a digital camera, you combine that, you average that, because RGB is enough to generate all the colors in terms of what human eye perceive, right, in terms of our perception. And so that's more than enough to generate all these images which we see. And you can see there is more of green than red and blue, right? So it's almost, number of green pixels are double the number of red and blue. That is because of the response function I showed you of human eye. It's more sensitive to green. And so it's important to have more green filter than blue and red. Yes. So this is not for astronomical imaging. This is for a digital camera. Yeah, so but it's a small difference, 552. It's a 50 nanometer difference. Yes, typically you're assuming that is all optimized for the light background. Because if you remember, I don't know if you have seen a little bit older camera, if you take an image in the dark background, you get very horrible images. It wasn't stable because there were not enough photon. And so imaging in dark is a hard thing. Digital camera is optimized for the light conditions. Right. So this is the kind of filter, which is why you don't have to take multiple images of the same thing, and then if you're collecting if you're taking an image from digital camera, you can just spot it, take one image, you collect all these 3 light, represent it in different color. For our eye, that's more than enough. But it's missing a lot of information, right? It's only using these 3 rough wavelength and information around that, and that's not good enough for our purpose. If you want to do astronomical observations, that's not good enough. We cannot use a mechanism like this for astronomy. Yes. Yes.
Isn't that important? Because what kind of science we want to do is also related to what resolution we require.
So by resolution, you mean the wavelength resolution? Yes. So what wavelength resolution you want to use is connected to what kind of science you want to do. That is true. That is something I will come back to it. Right. So that was the Bayer filter used for digital camera. For astronomy, we have similarly a list of filter which has developed over the years. And anytime you're looking at any data, you'll see these terms. So any catalog you're looking at, you'll see magnitudes in U band, G band, R band, I band, Z band, or whatever, depending on what system it has come through. And so there are lots of them, right? So if you go and look at any data, this is how you understand it. Is basically when you look at these bands labeled by different system, each of these bands have a response function as a function of wavelength, and they are showing you, they are giving you what is the total light collected in some standardized unit in those bands. So you can reconstruct the light you have observed. One of the most common filter is this UGRIZ, which I showed you on that composite cartoonish image. This will get like huge amount of imaging data in this system, which is similar to UGRIZ, slightly different, plus also have a Y filter pushing it a little bit more into the infrared, right? And then there are other, so these are sort of few order of 4 to 5 filter covering all of optical and a bit of infrared. Now we are getting into the age where we are something we call narrowband filters. So we have more than few. We have order of 12 or 40 filters. And then if you take it to extreme regime where you have many filters, then you basically in the regime of a spectroscopy. So if you have 5,000 of filters in optical range, then you are in the regime of spectroscopy. And when you are doing spectroscopy, you don't do filter, you do it differently. And so we'll come back to that as well. Right. So this is a response function of all the filters I showed you in terms of optical, as well as many additional response functions. So if you look at UV, any kind of UV telescope or UV data, these are the 2 UV, far UV and NUV filters. So for example, if you have heard of AstroSat, AstroSat had FUV and NUV, and Galaxy is another mission which also has NUV. These are the filters. So they were sensitive to this part of the wavelength, and this was the response function. All of this I've plotted in a Gaussianized version, so they don't have the exact form. If you look at the exact form, there are more details. So for the illustration, I'm plotting just some sort of a Gaussian representation of the same thing. This UBVRI is the typical optical filter. Most of the optical data will be in these bands. You can go to infrared. So there is a telescope, WISE telescope, which is a space telescope sent by NASA. We did a full sky survey, which had these 4 bands, W1, W2, W3, and W4. And then if you, let's say you're thinking about future mission like SK low, SK mid square kilometer array that goes to the radio wavelength. And so these are the essentially regions which is going to cover in terms of the wavelength. And our own GMRT, the upgraded GMRT, which had some improvement in terms of the band, it has these band 2 to band 5, and these are the representation of these bands. And so actually this is the most critical information if you want to sort of figure out what science you can do or what kind of scientific analysis you want to understand. If it has anything to do with light emission as a function of wavelength, or interaction of light with, let's say, dark matter as a function of wavelength. All this information is what you would need. You can also observe the sky in X-ray band. So there are several X-ray missions has happened. One of the most recent one is E-Rosetta X-ray mission, and so that covers roughly this region. And you can observe things in gamma ray. So this essentially covers all of the electromagnetic spectrum. Of course, there are beyond electromagnetic spectrum measurements now. For example, gravitational wave, which have a response function in terms of the frequency of gravitational wave, which is not shown here. But this covers most of the electromagnetic spectrum. So if you're thinking about galaxy survey, you are taking data in one of those filters. Now, the issue is in this kind of survey, now you're not taking data in all filters simultaneously, right? So you have to take one filter at a time. You want to apply the filter, take the data, and then expose it for a certain time, and then apply the another filter. So if you have n filter, you need to essentially do n times. You have to survey the sky n times. In principle, you might think, okay, let's collect data in all filters, but then you want to optimize. Do you want data in all filters for the kind of science you want to do? And so a lot of these optimizations, I'll tell you how sort of roughly we go about this as well, needs to be done when we define a survey. So anytime you read a description of a survey, they will say, oh, we'll observe in x degrees square of the sky in 3 filter up to the depth of x, y, and z in these filters. So often this will look some sort of a random choices they have taken, but these are not random choices. They have optimized it for certain science cases. What are the gaps? It's just that we don't have any filters in those regions. So this is a continuum in wavelength. In principle, you can, but collecting light of all different wavelengths is not as easy. Optical is typically considered to be easiest. Now, the design of a radio telescope is very different from the optical, because if you want to collect photon of centimeter and meter length in radio, you have to design very different instrument. And so these regions haven't been explored that much in terms of the, so this is far infrared, it's fairly hard to do. And then also in terms of X-ray, the wavelength, the kind of telescope you design for X-ray to collect X-ray photon is very different from something like CCD I showed you. Right? So what I showed you is mostly this part. These things have very different design. And so in principle, photon exists and you should be able to design a filter, but design a detector first of all, and then do that. But yeah, we have not done that so far. Yes. So I have Mm-hmm. Sometimes. So, like, how we do this thing simultaneously when we, for example, I'm looking at this 500 VCR. Mm-hmm. So, how these filters are like very time scale so that we get the information like there. Right. Yeah. So that's a great question. If you're interested in transient science, right? So things which are changing, then you have to be a bit more careful about how you want to do it. Because then you need to fold in the time scale of the change, and do you need images in all different bands at the same time? You have to ask questions like that. So typically when we design this filter, we actually, the images taken in different bands is widely separated. We don't take immediately after one another. SDSS was the only survey where the detector was designed such that in different filter you take images right one after another. But all other survey, we say whenever we have access to a certain part of the sky and condition is good, we'll take image in certain filter and we prioritize one filter over another. So the time variability is not folded in the survey most of the time. If you want to sort of look at transient, then often you are sort of happy that transient is detected in even one filter. And then if it is detected, then you have to observe it's anyway going to disappear. So you either change the mode of operation and you say, okay, now I'm going to observe this transient in all filters, or say, okay, I'll take another telescope which is much bigger, much better, and I'll observe all this thing is transient. So you do that kind of operation, and so there's a lot of sort of active movement needs to be done in variable sources and transient cases. When I'm talking about designing these kind of things, most of the time you're not thinking about variability. You're saying that these sources are as it is in terms of the time scale of the survey. Like 5-10 years, they'll not change. Okay, so now if you sort of look at different kind of galaxies and look at emission of these galaxies, so this is a particular illustration from candle survey in certain range of wavelength. If you look at, for example, a spiral galaxy, which is shown in green, versus elliptical galaxy is shown in red, you'll see that there is a difference of SED, right? So the green has much extended SED and red has much lower flux at a smaller wavelength. And so let's say your goal is to distinguish between these two, then you should target that you want to be able to measure this region as well as this region, in which case in one of the part of the wavelength you'll see the red galaxy, in another you'll basically not see because the flux almost goes to zero, but if it's a green galaxy you'll still see that. So you have to look at these kind of things and then design what kind of filter you want to observe. If it's a AGN or a quasars, which is shown in black line, you can see the flux at infrared wavelength is much higher. So for example, the WISE survey filters I showed you, it has the largest catalog of AGN because it's sensitive to those wavelengths compared to any other survey. And so you go back, now this is about galaxy. So you go back to your galaxy formation model and think about, okay, what kind of things I'm still interested in understanding, what kind of variability it produces in terms of the spectral energy distribution, and then what kind of information I want to gather to answer any question, how do these galaxies form and evolve, what is the role of black holes, and blah, blah, blah. Right? So you do that. And this is why it's important. So these galaxies will have different brightness. It's not at all constant as a function of filter, and so you want to collect multiple filter information in multiple filter. But beyond that, so that is not so, that is more on the galaxy formation side, but in terms of cosmology, what do you need to know? So to do cosmology, largely what we are trying to do is that we are trying to trace the distribution of dark matter inherently. This is what we want to do. We want to look at how the dark matter is distributed, and that answers all, that gives you answers to all of your cosmological questions. So, and then I told you yesterday that you can assume that to a great extent at large enough scale that galaxies are tracing dark matter. And so if I make a map of galaxies, I can create a map of dark matter at certain scales. And so if you want to create a map of galaxies, as long as you detect galaxy in any of these filters, you have the position of these galaxies in the sky. So that's the 2-dimension. But what you're missing is the 3rd dimension, and that's where the cosmology-wise filters are important. You also want to measure distances through these galaxies. And so what do you expect in terms of distances? As the light from any source is emitted, it's going to travel, right? So it's going to start traveling. Now, it's going to have lots of interesting effects on the way. So one of the things it's going to encounter is that the light is living in a gravitational potential well of some dark matter distribution. The light has to climb out of the gravitational potential well of the dark matter distribution, so it's going to get a gravitational redshift. So let's say there is some process which may emit a particular line, oxygen 2 emission line in the galaxy. Now that oxygen 2 location of that is going to get shifted. And if you can measure this shift, you can actually probe what is the potential well this galaxy is living in. And you can, if you know the potential well, you can estimate masses. If you break a weak equivalence principle, then you can sort of test for that kind of thing. But beyond that, what's going to happen is that this light is going to sort of start traveling in free space, and in free space now we are living in an expanding universe. So in an expanding universe, that's going to get stretched, and hence any wavelength is going to get shifted or redshifted. So for example, if this emission line is emitted at this wavelength, it's going to get redshifted by the time we observe it as it travels through the space. And then this shift is something very important. So this shift is what we call essentially change in wavelength is a measure of redshift. Right? So that's the quantity probably all of you have already heard of. And so we can measure this delta lambda, and if we know what kind of line it is, we know what is the true emission wavelength of this from our understanding of quantum mechanics, we can measure redshift, which is delta lambda over lambda. Now, in our understanding, redshift is related to scale factor, right? So the scale factor is the quantity which quantify how the universe is getting a scale as a function of time. So the scale factor is what is essentially causing the redshift. And so if a galaxy light you're going to observe emitted at time t, the scale factor is going to be related to redshift as a of t over 1 plus or 1 over 1 plus z. So by measuring, if we can understand how the lights are getting shifted, which means now you need to require at least 2 bands to observe something shifted, or probably more. So you need to think about what kind of resolution you need to measure redshift, and then there are various degree of uncertainty at which you can do that. You can measure scale factor. The scale factor is very interesting quantity, but before talking a bit more about scale factor, I showed you these sort of narrow broadband filters. So these are called broadband photometry, all the filters I showed you. But now what's happening is that because of this redshift, people realize that we want to measure redshift at certain precision, and these broadbands are not good enough. We want to have more number of bands. But when you do more number of bands, of course, things are going to get more expensive. So there are 2 surveys, POW and JPAS. These are basically trying to do 40 bands rather than 5 bands in the optical. JPAS is trying to do 54 band in the optical and infrared region. And there is one survey called SphereX, which is going to be in space. So it's going to be launched by NASA most likely next year if nothing gets delayed. It's going to have 425 bands covering all the way up to pretty far infrared, right? So you can use that information. This will allow you to track these changes that I'm talking about in terms of any sort of emission feature to a higher precision and give you a better estimate of redshift. That's one of the things. Of course, you can talk about all the other galaxy formation, which I mentioned earlier. But for cosmology, redshift is the critical importance. If you know most of the survey, so one of the way to measure the content of the universe is weak lensing. I'm not going to talk about weak lensing, but there, in fact, in this IAGRG series, there is a weak lensing lecture series you can go and look at. Right now, one of the most biggest issue in terms of the weak lensing, which is limiting the precision of any of our measurement and model testing, is the uncertainty on redshift. So the 40Z error is one of the dominant thing which we are trying to do. And so these are the surveys designed to sort of think about how to improve that. But you can also pretty much go to a very different regime, which is spectroscopy. So in spectroscopy, in place of 40 or 54, you're going to have thousands of filters. And so now you're not going to do it in filter. Now you're going to do completely different technology, which is spectroscopy. I don't know if any of you have done any experiment in spectroscopy. So you're going to take the light and split it as a function of wavelength by a dispersion mechanism and record as a function of wavelength. And there you're going to do thousands of these detectors. So this is 2000 to 4000 for DESI. For PFS, it's about, I think, 4,300. And for SDSS, this is an old survey, it was 2,500. So you can do broadband photometry, you can do this narrowband photometry, and you can do spectroscopy. All of this will have different cost and different advantages and disadvantages too. Right. So one example of a spectroscopy is these are the spectra from DESI survey, going from something like so this is the range of wavelength. This is going from very low redshift to very high redshift. The end of it is around redshift 0.5 or so. And what you're seeing is DESI has observed different kind of galaxies in different redshift regime for various reasons. And you can see that there are many features in these spectra, and these features are getting shifted in systematic manner. This is what we are talking about. So this is essentially the evolution of A of t, scale factor is what we are trying to trace. Right? So for example, this is O2 line. This is emission line galaxy, which has bright star formation, and these are oxygen 2 line, which is getting shifted. These are quasars, and these are Lyman alpha and Lyman beta lines, which are getting shifted. Right? So you can see there are many this feature. You can use any of these lines. What we use is we use all the information about spectra to figure out what the redshift is for individual objects. And so why it is interesting, just very quick illustration, if you have to have a lambda CDM, and let's say if you also know, apart from redshift, if you know what is the distance of this object, and we'll talk about how to get the distance, you can plot essentially, you can convert that into look back time, and you can plot how the look back time is going to get shifted as a function of wavelength. So these are the two models. The solid line is lambda CDM, and dashed line is a dark energy equation of state, which is W is different from -1. There's a non-zero, -1 W naught and non-zero WA. You can see they can distinguish these two. Of course, this is calibrated to a particular model like lambda CDM because my y-axis is just bogus right now. Sort of in the sense that I just calculated from the theory, so it's perfectly falling on the lambda CDM line. But so you need to figure out an independent way. So what you can measure is the redshift, but you can need to figure out an independent way to measure what is the distance or the look back time of these objects, and that will allow you to constrain things like dark energy equation of state. And so that's very critical. So a little bit about spectroscopy. So in terms of spectroscopy, rather than filter, what we do is we take light from a particular source, and so that's important. We take light from a particular source, we pass it through gratings. So grating have this essentially division, which are in older system, this could be a prism, right? Prism also disperses the same kind of thing, but we use grating. And then what it does is that it spreads the light as a function of wavelength, which then get focused and collected on a detector. So now you have intensity as a function of wavelength. But there's a key difference here compared to previously. Previously, we were saying that we'll just open the shutter to the sky and we'll observe whatever it is. Now we are saying that we take light from one source and then do all this. Right? So that's a very different thing. If I just open the shutter and light from all source will come, then I will have hard time figuring out which galaxy has what wavelength, what intensity at what wavelength. And so that's a very key difference, which is why in the plot I showed you in the previous lecture, the spectroscopic samples were always factor of 10 to 100 is smaller. Because now, first of all, you have to do this detail split, but you also have to do source by source. So before even doing that, you need to know where are the sources, right? For the previous step, you don't need to know where are the sources. You just open the sky, wherever there is source, you'll observe. So you have to do a photometric survey first. Then you have to figure out, okay, what are the objects you want to observe spectroscopically? Then you can target those objects and then do this measurement. So spectroscopy is much more expensive. It has more information, but it's much more expensive. That's why number of objects is always going to be 1% of the sample. Like if you have 100 objects observed in the universe in terms of the imaging, you'll have probably one of them with the spectroscopy. So that's the ratio you're working with. Okay, so now some detector comparison from the spectroscopy side. If you look at the value of R, so what is R? R is the number of division you have in terms of the wavelength as a function of wavelength in the detector for whatever wavelength coverage that instrument has. So if you divide the range of wavelength by R, you'll get the resolution, average resolution of wavelength. But of course, this is not constant. This changes in the realistic system, so you need to keep track of that. But roughly, if you look at how different R looks like, and so you can start with human eye. Human eye is an amazing instrument. It does both imaging and spectroscopy to a level at each pixel simultaneously, right? So we take the image, but we also know the color. I can see all the colors as well at the same time. So of course, it doesn't do it doesn't win in terms of our instrument anymore. But if there is so this is in the unit of velocity kilometer per second. So we are basically representing wavelength resolution in terms of the unit, right? Because wavelength will give you a conversion to velocity. And so if you look at two galaxies by eye, they are moving at 1,000 kilometers per second, and they say they're exactly same intrinsic color, and you'll see it by eye, you'll be able to detect the difference. That's what this means. So if the two galaxies are moving at a relative velocity of 1,000 kilometers per second, they are intrinsically exactly the same. You'll see that by eye, they're actually different, if you can look at that. And so that will give you a delta lambda, which is roughly 2 to 5 nanometer for eye. Right? So these are just rough number. if you look at previous generation survey like SDSS BOSS, which was done around 2012 or so, that could detect these thing at the level of few hundred kilometer per second. That's the resolution. And DESI can do this at the level of 70 to 80. Of course, this will depend on more detail. These are just rough number. It will depend on the type of galaxies and type of lines you're observing. But it's roughly 100 kilometer per second. And then there are like some very high resolution instrument in terms of very high resolution R. And you can detect differences of 1 kilometer per second. 1 kilometer per second is really a remarkable thing which they can do. And it's a very hard thing to do. There are so many instability in a system like this that 1 kilometer per second is very hard. But why are they interested in 1 kilometer per second? These things are particularly designed to observe stars in our Milky Way, because stellar atmosphere and stellar activity is not of the order of 100 kilometer per second, but more like few kilometer per second. But if you think about typical galaxies, Milky Way kind of galaxy, what kind of velocity dispersion these galaxies are going to have, they will have order of few hundred kilometer per second. So for cosmology survey, so for example, DESI is a cosmology survey, this is more than enough in terms of, so practically your errors on redshift at this level doesn't matter for cosmology. All right, so this is the same thing, but in terms of a table. I've already told you all the numbers, and then but now I am also showing the coverage in terms of the wavelength, the R value, and sort of rough years when these instruments were started observing as a function, and compare that to the rough number for human eye, 2 to 5 nanometer. And this thing, but one of the key differences is that human eye also sort of do the spectroscopy at each pixel rather than only at certain locations. Okay, so I guess I sort of roughly talked about 3 different kind of observation you could do depending on what you're interested in. You could do broadband photometry, which is roughly what we always do most of the time. You could do narrowband photometry, which has become possible very recently. The first survey is just happening, and we have not had any cosmology results so far for this survey yet because the data is being collected. And 2 more like really massive narrowband photometry survey is happening, one from space, one from ground, and so in the next few years we'll see results from those. And then you can do spectroscopy, and we have been doing spectroscopy for like since 1980 or so. In fact, even before Slipher started doing spectroscopy, through which Hubble was discovered, right? So I mentioned that. But now we are doing it at massive scale. So you can do spectroscopy and measure spectra and measure very precise redshift of these objects. Right. So now that you have these choices, now you have these choices. Now you need to ask, essentially, what do you want to observe? So do you want to observe a small patch of a sky, but to great depth? You want to observe large part of the sky, but only few objects, because total time is limited, right? I mean, in principle, you can observe everything if you spend hundreds of years, but let's say you want to do this in 5 years or 10 years. You need to choose, you need to make choices like this. So you need to make a small part of the sky or a big part of the sky, and depending on that, your depth will be decided. Right. Also, you need to ask yourself, okay, what are the key things for your science case? Is it that the number density of this galaxy important roughly, or how well you needed to know the redshift? Do you need to know the redshift very precisely, or narrowband photometry is enough, or even a broadband photometry with 3 band will be enough, right? What is it sufficient to achieve your goal? And so these are the questions you need to ask pretty much for anything. And often what happens is that whenever we're designing an instrument or survey, we start with one science case and we optimize it for that. But then once it's done, we try to then diversify. We try to see, okay, what are the changes I can compromise so that I can do many science cases? Because these are expensive missions and long time. You don't want to hyper optimize also. So that is also something you need to keep in mind in terms of diversity of science cases when you're looking at a survey like this. So let me talk a little bit about now the scale factor. So this is just to give you an example of how to do this for one particular scenario. Right, so all of you are familiar with the scale factor, I guess already, right? By now, there are several things. But why is the scale factor important? Especially, let's say, if you're thinking about dark energy or Hubble constant, if you want to measure Hubble constant, what kind of survey you want to do if you want to figure out, depending on what quantity you measure, to give you 1% measurement of Hubble constant. Let's say that's a question, right? So first of all, scale factor A of t is one of the fundamental quantity which we would like to measure to understand energy density of different component of energy in the universe, and how these things evolve. So if you know the content of the universe and you know the scale factor, you can determine what the energy densities are. If you know the energy densities, you know the scale factor, you can determine what are the content of the universe are. Either way, you can use Friedman equation and convert. But just for the illustration purpose, let's say I'm going to write a scale factor as a essentially a Taylor series, just to see what is the effect of first few terms. Let's say we are considering only the first three term of the scale factor, and we ignore all the higher order term. In general, scale factor need not be represented by first three term, but first three term is enough to talk about acceleration. So that's why I'm limiting it at first three term. You can sort of simplify this by all right. So yeah, so let's actually set AT naught equals to 1, right? So that's the scale factor today equals to 1. So that's our convention. If you set AT naught equals to 1, you can write this down in this way. And in fact, we know that Hubble is nothing but A dot, and you can write acceleration parameter. So you can write this A of t as 1 plus h t minus t naught. I might be missing some constant factors and things like that, so ignore that. Yeah. So you basically what you get is this is the definition of Hubble. This is how the deceleration parameter is defined. You can work it out given these two relation, what the Q naught is exactly. And you see a negative sign because we are talking about deceleration parameter. This is how it was introduced because we thought earlier that universe will be decelerating. So when Q naught is positive, then universe is decelerating, right? So now let's say, I mean, I can do the small approximation and say, so why do I want to write 1 over A of t? So one thing you want to figure out, let's say I can observe the proper distance of objects dpt is going to given by, so this comes from the Virmani equation, right? So I can write this down. Essentially, proper distance is the integral of a scale factor. In the universe where A of t is just 1 everywhere, it's basically c dt, right? So just time speed of light times velocity. So I want to write 1 over A of t, and based on that, I can do a small value approximation, and I'll get something like this. Yeah. So if you plug this in dp of t, you're going to get or I can just do the, so let's say this integral is te to t naught, this is dt t to t naught, it will be t naught E minus T naught. And then you'll have. So if I were to be able to measure dp of t, let's say all the light I'm observing from this galaxy, somehow they are tagged in terms of the time it is emitted or the look back time t minus t naught, then by measuring this kind of thing, I'll be sensitive to both Hubble constant as well as deceleration or acceleration q naught parameter. So this is why we are interested in things like measuring distances of these galaxies. But unfortunately, we do not have anything which directly tells us the look back time of a galaxy we look at. Right? So we do not have that information. But what we have is we basically have redshift. So by looking at the galaxy, and if we have information in the enough band, we can determine redshift to certain precision. Right? So with a narrow band, broadband, or spectroscopy, and this will essentially give you. So redshift is related as because earlier I told you, right? A is equals to 1 over 1 plus z. So redshift is related to the scale factor. And so what we know about each of the galaxy, we know redshift or equivalently scale factor, but we do not know that look back time. And so now we need to sort of think of a way to measure distance in another way. And we already have redshift information for these objects, right? Yes. No, this is not assuming that we are going. Not. It is just assuming that a scale factor is represented in this fashion. No. So in principle, yeah. So what I'm saying is, if you look at any reasonable model, scale factor is actually a very smooth function. So this is not a bad representation. But let's say you want to think about models where things are not represented by that. That's also fine. You can do this calculation, and you don't need to make this approximation at all. You can actually do the full integrals, right? But it's just that when I do this, I can explicitly tell you that there's a h naught and q naught. But in reality, we don't do this. We don't do this approximation at all. This is only to show explicitly that there's a h naught and q naught dependence. But even if you don't write it in terms of the Taylor series, if you write the full functional form, the same h naught and q naught dependence will be there, which is what is used in the real analysis. And so the distance are sensitive to Hubble rate as well as any acceleration deceleration universe is facing. Okay. Yes. This one. So I just set AT naught equals to 1, right? And then this is basically the convention. And so based on that, now you can define your H. H is essentially A dot. And H is A dot by A, but A is, yeah, A T0 is 1. Yes. Yeah, so you only set AT0 to 1. Okay, see, let me see what's in my notes. Yeah. DADT is T equals to T0. So this is all T equals to T0. So this is H naught, yeah. So this A T0 is equals to 1 basically. And here also it should be a 0. And then similarly you can define Q naught by essentially taking this A double dot and H naught relation. Yeah, thank you. All of this is at derivative at T equals to 0. So that solves the thing. Okay, so now we know that we can measure the distances, and we know that if we can measure the distances, we are sensitive to Hubble rate, expansion rate locally, as well as any additional second order term like acceleration or deceleration, right? But we can measure the redshift. I already illustrated that, and we can measure the scale factor. But how do we measure distances? So we measure distances through essentially something called, so there are two broad ways of measuring distances. One is called luminosity distance. So if you think about a source, which is a standard candle, right, emitting light at some known luminosity. So this is an example of supernova. Let's say we already know what is the luminosity of this source is. Measuring luminosity is essentially measuring distance. Why? Because what you can measure is flux, and the flux is going to be, in a very simple case, 4 pi r square, right? So if you know this is something you can measure flux, if you know the luminosity in the band, you know the distance. But this is not true in terms of how our universe is working, right? So because we are living in an expanding universe, I cannot just do this 4 pi over r square. So first of all, you have to write essentially the metric, which is, let's say I'm using a particular convention for the metric. Right, and then you can write basically S kappa depending on curve. You're looking at flat universe or positively curved, negatively curved. It will be sine or sine hyperbolic functions. I'll not write that, but in general, what this is going to give you is that area at certain r is essentially 4 pi S kappa square rather than just r square. So that will be the first change. So the flux is going to be this is what you are going to observe, and so you are going to measure S kappa, which is essentially the proper distance. But that's not all. There's going to be two more things happening. One thing is, if you imagine that, let's say this luminosity is at some fixed wavelength for the simplicity, which is lambda e. Let's say this object is emitting at lambda e. And so this lambda e, by the time you are going to observe, will get converted to lambda O, observed wavelength. And this transition is something which we can write down, right? So lambda so this is essentially definition of scale factor or redshift. Delta lambda over lambda is redshift, and you just translate that, you're going to observe different wavelength. Now, since A is equals to 1 over 1 plus z, this is essentially lambda e times 1 plus z. So what this means is that if you think about essentially energy of this photon, which is what we are sensitive to, energy of the observed photon is equals to hc over lambda observed, hc over lambda emitted times 1 plus z. Sorry, I should not have written here. It's 2. This is basically energy of the emitted photon divided by 1 plus z. So just in terms of the energy, which is what you'll be observing in terms of flux, you'll get a factor of 1 plus z there, additional factor. There's going to be another thing, let me do it here, which is, let's say if the light emitted, there's a series of photon which is emitted at some delta TE separation, which means they will be separated by c times delta T in terms of the distance. Now, this thing is going through the expanding universe. So this distance is also going to get expanded. And so by the time it approaches us, this will be essentially also gain a 1 plus z factor. So which means the photon rate you are going to get, which is what also goes in the luminosities per unit time, right? So per unit time, per unit area, that will give another 1 plus z factor. And so all of this combined, the new flux is going to be square. And now let's say if you equate this to essentially there is some sense of distance which I will call luminosity distance 4 pi dl square. This will give you dl is equals to s kappa r times 1 plus z, or in another way, it's dp times 1 plus z. So if we know the luminosity of some standard sources, and we can measure that, we can measure the redshift as well, we can measure the luminosity distance, which will be related by the proper distance with 1 plus z. So once you have the proper distance, now you have both redshift and distance, you can figure out H0 and Q0. So this is one of the way, this is what the supernova cosmology is all about. There's a lot more things goes on in terms of the standardizing the luminosity itself, which I'm not going to talk about, but in the spirit of sort of thinking about, okay, how you can use this to constrain that. So another very quick thing I wanted to go over, because I'm running out of time, but let me do this very quickly, is angular diameter distance. Right, so dA. Now imagine a scenario where you, in place of a standard candle, which is what the known luminosity is, you have a standard ruler, which means, let's say you have a scale, and you know the size of this scale, L, and this is known. This is well known from some standard physics. This is, I'm actually referring to BO, and I'll come back to how we know this and how we measure that from fundamental. But for the purpose of distances, let's say you know this size. Now, what's going to happen is that you're going to, essentially the light is going to follow null geodesic, and there's going to be delta theta associated with that, right? So in this case, what you're going to measure, and if this distance is dA in this kind of picture, then dA is equals to L over d theta. Okay. So in the limit of a small angle. Now, again, in terms of the metric, which I already wrote, if you think about the only thing changing is the d theta part, then it will look something like this if I were to write that, d theta. Okay, so ds, which you can take it from there, everything, all the other d's are 0, it's only d theta survive, so you'll get a relation like this, you'll get a factor of scale factor. Now ds is known with L, so I can substitute ds with L, and d theta is there, so I can essentially write L over d theta, which is equals to dA, angular diameter distance, which is essentially AT times sk over r, and A is nothing but 1 plus z. So angular diameter distance is So now we have two ways to measure distances. One is, if we know the standard luminosity, you can measure luminosity distance, which is proper distance time 1 plus z. And if you know a standard ruler, you know the size of some object which you can see across the universe, you can measure angular diameter distance, which is proper distance over 1 plus z. Okay, so these are, both of these things if you can measure, then you can essentially constrain dark energy equation of state or Hubble rate kind of quantity directly by this kind of measurement. So this is just in terms of slide, the same thing. If you have a standard candle, and if you define the proper distance, you can measure the flux, and the flux is essentially which will be related to luminosity distance in this manner. All right. And so this is what supernova and standardizable candles are. And then I have also, in terms of slide angular diameter distance, if you know the standard ruler, which is BAO, you can measure the angular diameter distance L over theta BAO, which is related by 1 plus z factor again. And then we also define another quantity called dm of z, which is same of dp of z, angular diameter distance. In this case, we are also going to be able to measure, let's say if you know this scale not just perpendicular to you, but parallel to you. If you align this scale parallel to you, then that is going to give you some fixed delta z in terms of the scale. And the BO you can measure both across and perpendicular. And then that will give you what we call DH of z. All right, so the DH of z and dm of z is what you can measure as a part of angular diameter distance, or you can also measure the isotropic part of it, which is dv of z. All right. So this brings me, so in last 15 minutes, I wanted to just quickly go over Fisher forecast as a tool to understand how to do this thing. So I've told you that in surveys, you have to think about filters, wavelength resolutions, spectroscopy versus different kind of photometry. Now, if you doing either of that, you can get an estimate of redshift, which is an estimate of scale factor. Along with the scale factor, if you can also measure distance by some other thing, luminosity distance. For example, if you know the precise flux, you know the luminosity distance, if that is standardized, or if you can measure BO as fixed scale. And I'll talk about BO a bit more later. Now, let me ask a question, which is that let's say you want to measure Hubble rate to 1 precision, or equation of a state to something precision. How do you figure out at what precision I need to measure these distances, angular diameter distance or luminosity distance? For how many objects at what precision, at what redshift range I will measure such that I will get something like 1% precision for Hubble rate? If you want to ask this question, or any such question for whatever science you are interested in, you can use Fisher forecast to answer questions like this. Okay. And then right now I'm only talking about the distance level, but then you can go further and talk about in terms of the photometry level or the spectral level thing. So you can generalize this further. So Fisher forecast is essentially a tool which can predict precisions of parameter without really doing the experiment, if you roughly know how the errors would look like and how the models behaves and for these parameters as you change the parameters itself. And it is widely used in cosmology and planning survey. So what we are really trying to measure is, we are trying to measure is what is called Fisher information matrix, which is defined as following. So let's say you have a likelihood. So you have a way to define what is the likelihood given the data for a certain parameter. And so you can define this function, which is essentially the derivative of log likelihood with respect to the theta. The thetas are your parameters. So for us, it will be H naught or Q naught can be our parameters. And so you can take this derivative where the likelihood itself is essentially the measured quantity minus the model predicted quantity divided by sigma square, right? So the chi-square is same as the log likelihood in the Gaussian assumption. If you take the expectation value and so this is a particular, yes. Mm-hmm.
Physics, what is the difference if Fij has offline terms or if Fij is diagonal?
Right. So if Fij is diagonal, which means let's say you're considering 2 by 2 matrix, where the size of the matrix is basically number of parameters, right? So if you have 2 parameters, you'll have a 2 by 2 matrix. If you have 2 parameters and you find that Fij is diagonal, which means these parameters are uncorrelated, in the sense that in terms of the physics, I can change one parameter by large amount or small amount, the other parameter doesn't get affected at all. It's not the changes. So changes in whatever you're observing is uniquely decomposable, essentially. That's what it means. So whatever, let's say I'm measuring distance, I should be able to measure decomposed distance in certain way that one part of distance is affected by only one parameter, other part is affected by other parameter. That's what it means if it's uncorrelated. If it is correlated, which means they are coupled, which means I can change one and produce somewhat similar effect as changing other. And so when you can essentially convert this and make a plot of this posterior I showed you, right, 2D contours. And another way to make the same statement, when you make this kind of posterior, if they are diagonal, then it will be circular or elliptical, but aligned to one of the axes. But if it is not aligned to one of the axes and elliptical, then that means they are off diagonal. So
if you propose a model and the model parameters are very strongly correlated, is it wise to introduce both the model parameters as one can actually incorporate the change of the other?
So the wise is probably a strong word to use, but your question is about whether if the parameters are strongly correlated, you can probably write it as one parameter, but then your model is different, right? Now you're saying that these two parameters are equal. That's a different model than two having a degree of freedom. If they are perfectly correlated, then that means the model that is sort of very hard, almost impossible unless they are exactly the same. So there can be strong correlation, but they cannot be perfectly correlated. And so you need to figure out how to decompose this in a more efficient way. Maybe you can reparameterize this such that you can now write down new parameters which is uncorrelated. And so that's the kind of thing we often do when we find strongly correlated parameters. Yes, so I mean, for Fisher it doesn't matter so much, but when you do actual analysis and the parameters are correlated, then that becomes hard in terms of probing the space. When you're doing a Bayesian posterior likelihood, you're trying to sample the posterior distribution. That sampling becomes hard, and so you can reparameterize it whether it's positive, negative. If they're strongly correlated, you can essentially do, let's say, eigenvalue decomposition and write down a linear combination of those two parameters, which are the two new parameters, and they will not be correlated anymore. That will simplify your analysis and interpretation when you're doing this kind of thing in terms of sampling. For Fisher, it doesn't matter that much. Yes, so this is essentially averaged over all of your data. So you don't have just one measurement, you have many measurements, so it's averaged over all of the measurements you have. It might be even different kind of measurements. You might have luminosity distance and angular diameter distance, both of them. You can average over that. Okay, so now the Kramer's law bond, what it says is that when you do this kind of Fisher information, it may not be it's never the exact number which you do get after doing the experiment, because a lot of things are simplified, but it actually sets a bond. And so it essentially says that this is at least this much. The error will at least be this much, it might be higher. It sets a lower bound in terms of how much is the error is, and that's what we are sort of trying to get at. You cannot do the exact estimate of how much your error is going to be, but you set a lower bound on that. Right, and so I'll probably skip that in the interest of time, but basically you're saying that we often think about likelihood as Gaussian likelihood, so we Gaussianize the quantity we are looking at, we ignore the non-Gaussian term, and in the Gaussian limit, this is same as your covariance matrix of the parameters. Right, so all you need to calculate is the covariance matrix of your parameter in the given model. So application to cosmology, it's widely used. Let me directly show you this in the interest of time, but those are, you can look it up advantage and disadvantages later. And so now what I can do is that, let's say I'm going to do a survey where I will quantify it at the level of, I'm going to observe n supernova, and each supernova I'm going to measure the luminosity distance to a precision of 1%. That I can control by controlling my flux error, right? Because that's what is going in the simplified picture. Now, how many supernova I need to measure to have something like 1% precision if I'm marginalizing over all the cosmological parameters? So this is the exercise. So all I have done is I've taken these equations which we have looked at, luminosity distance relation, and I said, okay, I'm going to put an error on luminosity distance measurement, which is 1%. As a function of redshift, I'll cover redshift from 0 to 2, and I will say, okay, let's say if I observe something like 50 supernova, 100 supernova, or 500 supernova, and I'll calculate this derivative which I just showed you in Fisher information matrix. I'll calculate dl over the likelihood of dl over each of these parameters, and so now it's not in just one or two parameters, I'm taking pretty much all the cosmological parameters. And so if you were to do that and you want to achieve something like roughly 1%, which is the red contour what shows, you'll have to have something like 500 supernova, each one measured to 1%. So this gives you some indication of, okay, if you want to do a supernova survey to measure H0, what kind of sample you would be looking for, what kind of, it also gives you estimates. Since I'm saying 1% error on luminosity distance, it also gives you what kind of error on the flux will be tolerated to do this thing, right? So it comes back to all the quantity. I've assumed that redshift error is 0 because I've assumed it's spectroscopic redshift. But if you want, let's say if you want to do photometric redshift, you want to do n bands, you can also introduce a redshift error here, and then again do this thing in presence of redshift error, how will your error degrade? So this is how we typically design surveys for cosmology experiments where your science goal is one of those things. You could also say, okay, I'm not only doing just a supernova survey, I also want to do a galaxy survey where I want to measure BAO, and I'm claiming that I can do a survey, I know how to do the survey that I can measure BAO to 1%. This is not done regularly. BAO is measured to 1% in several samples. If I can measure BAO to 1% and I'll combine the information from all of them, what will I get? And maybe I can move things around in my BAO survey where I will look at different redshifts samples or different part of the sky, different volume and things like that. And so this is an example where I've done this exactly the same thing, but I've taken also angular diameter distance equations and looked at the derivative of this. If you were to do just the luminosity distance relation, that's the green line. The blue line is angular diameter distance measurement, BO measurement. And if you combine all of that, then that's the red line. So you can see now if you combine both of these things with this particular setting, you're getting pretty significant constraint on W naught, which is not there in the earlier plot. So you can just play with this and ask, okay, if I want to achieve particular thing in WA, or you can change the model. Say I'm assuming lambda CDM. Maybe you have some fancy model of something, or maybe some very interesting model of dark energy you want to look at. You can just change the equation which I've used in terms of taking the derivative, and you'll have your forecast. So this is the first order of thing. Now I'm assuming error at the level of these measured parameter of DL and DA. You can go further down and say, okay, you have error on fluxes in different bands and redshifts of these objects. And then how will that propagate to error on DA? You can again do the same kind of derivative calculations. And then how will that go in terms of the cosmology? This is also how we set the requirement that, we want to observe something for exposure time for so much in so band because that's the error I need in the flux. All of this is tractable. So I hope this sort of gives you that Fisher matrix is a very useful tool, and you can, in principle, think about how to use that to constrain various kind of contours and science cases in different model. One of the downside of this is that it always assumes a model. So you're basically measuring these things in a particular model. If you want to go away and your model is very different, the constraint might not strongly depend on the model. If the model is very different, then the error might change significantly, and in which case you'll have to do this in all different models. So what I'm going to do is that I'm going to send you a Python script which I used to, it's a small Python script which I used to make these plots and do this Fisher forecast for. Very simplified. There are lots of approximation in these scripts. So these are not research level thing which I'm going to send you, but you can get an understanding of, okay, how to do this operationally, what I just talked about, right? And run it by yourself and see different settings. If you want to put supernova in at different redshift or different precision, you can do all of that. You can also figure out, okay, whether a particular redshift is even useful or not, or can I throw away? Because dark energy started dominating only below redshift 1. Will beyond redshift 2 will be useful, or beyond redshift 1 data will be useful at all or not? That's the question you can ask. And in this case, it will be useful because it's not just dark energy, you're also constraining things like omega matter, which will be very well constrained if you go to higher redshift. But you can ask yourself and do that exercise yourself. I'll just send the script and you can try. I think given we have just 1 minute left, I'll stop here and I'll take any questions. Fisher matrix is non-invertible, but why would that be? It can be if there are strongly, I guess, if it's if perfectly correlated parameters are there, then it can be non-invertible. in which case you'll know that your model have some very strong degeneracies. You cannot invert it. Either you have to change one of the parameter or reparameterize things if that happens. For any sensible model, that should not happen.
We see different data points. So how do we decide that? I mean, sometimes we see from different surveys as well. And for the same kind of source, we see two different data at same brightness. So which one do we take? The biggest one or
Sorry, I don't think I understand. You're saying that there are two surveys and both of them observing in the same band. Is it?
Yeah, same band of the same source, and they are different. Maybe one came out first in 2023 and one came out in 2024. So how do we decide which one?
Then, so this should generally not happen, but then you need to ask, okay, how much difference they are, because both of these observations will have an error, right? And these are different realizations of the, typically exactly the same band, same source will not happen unless it's the same survey. And if it is the same survey, then there must be some difference between those two data points. For example, one of them might be longer exposure versus one of them shorter exposure. What is the difference? Is the difference much larger than the error they expect on those photometry or not? If it is not, then both of them are useful realization. You can take the one with a smaller error. But if there are larger differences than compared to error, then it's an issue. Then you should write an email to them saying, see, I've found these two fluxes of the same source, same band. They are different by 5 sigma. Do you know what's going on? In place of using one of them. Yes, so for supernova, this is what we do for the galaxy survey, which is doing supernova. But of course, the supernova is not exactly standard candle, and so we also have to standardize that. But in principle, if you ignore the standardization part, you're going to measure flux, and then you're going to convert that flux into luminosity distance, and that's how. Now you also have the redshift of these objects. So you have redshift and luminosity distance. So now you can write down in your model what is the redshift and luminosity distance would look like, and you try to do a fit. So this is what.
This is what we do for the supernova. I was wondering what are we going to do from using the data from the galaxy?
Yeah, so galaxy survey now you can do angular diameter distance measurement, right? So you can measure BO, and I'll talk about how you measure BO in the next lecture. But let's say you have a scale which you are going to measure, which is angular diameter distance, similar to flux, but it's not flux, it's much more complicated quantity. You measure angular diameter distance and you have redshift. So you have redshift and angular diameter distance, you practically have the same quantity with factors of 1 plus z. Now you can try to do the fit with the same model, and you can also do simultaneous. So this plot does, it's a Fisher forecast, but it does the same thing. It looks at the derivative and likelihood for each one of them and then do that simultaneously.